My name is James Bamba, and I'm doing the presentation for my research paper, which is Airport Pavement Design using a software called Federal Aviation Administration Rigid and Flexible Iterative Elastic Layer Design. In a nutshell, Faarfield. In this presentation, I'll talk about the layer properties or characteristics pavement of the pavement the software used to do the analysis. And then secondly, I will talk about the overview of the software, how the input parameters have been inputted into the software to analyze and produce results. And then on the third part, I will talk about a case study done in Western Africa. On the first part, this slide here shows the layer characteristics of an asphalt pavement. It has the typical asphalt pavement layer, the asphalt surface, the base, the sub-base, and the subgrade. The other materials like the stabilized base is used if the base is not strong enough, and the drainage and the geosynthetic separations are per geotechnical report. If the pavement located in an area that has a lot of water log, where the water doesn't drain quickly underneath the pavement, a geotechnical report might recommend using a drainage layer. And then if the subgrade is not strong enough, a geotechnical report might recommend using a geosynthetic separation layer. So again, this slide here is for the concrete layer. It's the only difference between this slide and the previous slide is the material on top. The previous slide we had an asphalt material on top, and on this slide we are having concrete material on top, but everything remains the same. And the other materials like the drainage and the geosynthetic separation layer are for geotechnical report. I saw recommendation based on the layer properties, based on the soil properties where the pavement is supposed to be built. This is the overview of the software. The software has like three areas, like the Explorer. This is where you put the input parameters, where you put the existing layer thickness. Like here, this is the existing condition at Banjul International Airport. We have the layer thickness here, 10 inches, 8 inches, and 12 inches. This is where you put everything. And then also, it has an aircraft area. This is where the software by default comes with so many aircrafts and they are loaded. This is why you put the aircrafts that it's departing the airport. We're using the departing aircraft here. That is because during departure, that's when the aircraft has its heaviest loading. So that's the area here. If you want to put the aircraft input, and then you have the material section. This is the material section is where we have the cross-section layers, their materials, what they are made of. So this is where you have the material section. So like I said, this is just an overview of the software. In doing my analysis, I use the existing condition here. If you see the existing condition, which I ran, and then I also had my proposed condition, and then proposed condition, I had one for reconstruction, which is this one here, and then also I had another one for overlay, which is rehabilitation. These are going to be discussed later. The existing condition. The existing condition at Banjul International Airport consists, like I said, if you look at the previous slides, consists of like 10-inch asphalt layer on top of cross aggregate and on cross aggregate of 12 inches with a California bearing ratio of 10. This is the existing condition. So these are the flights departing. These are the heaviest flight departing the airport, and that's the name of the flights here, and that's the gross weight, which by default comes from the software. And then this is the annual departure with a growth rate of 1.8%, which is really high though. So using the existing condition layer of the cross section of the pavement, if you use that and run for the thickness analysis, you'll produce a HMA cumulative damage factor of more than 1. The cumulative damage factor is used as a threshold in this analysis. A cumulative damage factor of less than 1 shows that the pavement is sufficient enough, and then a cumulative damage factor of more than 1 shows that the pavement is not sufficient enough. In this case, since our cumulative damage factor is more than 1, it shows that this pavement cannot support the loading coming into this airport for the next 30 years, because the 30 years is a design lifestyle that it's been designed for. So because it cannot support this loading, we need to find a proposed condition. We need to find solutions. So then the slides ahead will talk about the proposed conditions. On this slide here, again, this shows that this shows the aircraft that is causing the most damage, and this is the aircraft causing the most damage here. The B777-3ER is the aircraft causing the most damage, as it has the highest cumulative damage factor. This is a table from that represents the graph. This table represents the graph from the previous slide here. You can see again the B77-300ER having the highest cumulative damage factor. So going to the proposed condition, since our existing condition has failed, we have to do a proposed analysis. The proposed analysis, like I said, has to do with reconstruction. So the reconstruction means we have to reconstruct the whole pavement again with new layer thicknesses. So this is the reconstruction proposed condition. The asphalt layer, initial asphalt layer was 10 inches, so we're gonna bump it up to 12 inches. And then this time around, we're gonna have a stabilized base, because the area where this airport is located, especially in the raining season, experience a lot of rain. So we want the base to be stable. So we're gonna have a stabilized base of 8 inches with a cross aggregate of 6 inches and then uncross aggregate of 6 inches and a California bearing ratio of close to 8. So this is the proposed condition. If you lay this configuration into the software and run the analysis, the results are going to be produced as shown in the next slide. This slide here shows the result here. If you look at it, the cumulative damage factor is less than 1. It's way 0 even. It shows that it's brand new. So instead of 3.59 we had at the existing condition, now we have 0. So this shows that this pavement is brand new and it can serve the 30-year design life. Again, I want to give an emphasis to the subgrade cumulative damage factor here. This cumulative damage factor will never go more than 1, because this is the threshold for the subgrade. Once it hits 1, it shows that the subgrade is at a point whereby it's the limit it can take. So it cannot go more than 1 for the cumulative damage factor of the subgrade. But the cumulative damage factor for the HMA can go more than 1. And if it, like I said previously, if it goes more than 1, it shows that the layer is not sufficient enough. The other proposed condition is the rehabilitation, which is using overlay. So the initial condition of our pavement was 10 inches. So in this time around, we're gonna have an overlay. So an overlay, what we'll do, we'll mill the first 2 inches of the overlay. So when we mill the first 2 inches of the overlay, we're gonna be left with 8 inches. So the overlay thickness is gonna be designed on top of an 8-inch thick base, because we are milling 2 inches from the existing condition. Just to give an emphasis on this. From the previous slide, this layer thickness should be 8 inches. Taking into consideration the 2 inches of mill. Our initial design condition was 10 inches. So we milled the 2 inches and then we are left with 8 inches. So for the software to run an overlay design, it increases this layer to 13 inches to produce the minimum overlay thickness of 2 inches. This is a little bit tricky here. So again, I would say this layer should be 8 inches, taking into consideration the 2 inch we milled from the existing 10 inch. So 8 inch has been pumped into 13 inches to produce 2 inches of minimum overlay thickness. So now, if you look at this combined thickness, we have 13 inches plus 2 inches, that produces 15. So 15 minus 8, the 8 which is taken into consideration, the 10 inches minus the mill, will give us 7 inch. So the layer thickness, the overlay layer thickness, is 7 inches on top of a base surface of 8 inches. So that's the proposed condition for this overlay, for this section, for this rehabilitation section. Again, if you look at this, if you see this arrow here, it shows that the software can interactively do the computation internally and produce a result. In this case, for this overlay design, it can produce the minimum thickness of 2. This thickness here is not going to change. So what it does to produce a minimum thickness of 2, it changes this layer underneath. It changes this layer, which by default should be 8 inches. If you take into consideration the milling, it changes into 13 inches. And that's why it's imperative to combine these two layers, this 13 inches and the 2 inches, to produce 15 inches, and minus it from the 8 inch, which has already taken care of the milling from the existing 10-inch condition. So if you use this and you run the system, you're gonna produce a HMA CDF of 0.8, which is high, but it's still less than 1. So it shows that this configuration, like a 7-inch overlay on top of an 8-inch asphalt base, the remaining characteristics of the pavement, they remain the same. We are not impacting none of them. Should be sufficient enough to support the loading for the next 30 years. In conclusion, the Fairfield software is used to design pavement design, and in this case, it's used to analyze a case study at the airport, and it shows that the current pavement at the existing airport, it will not be sufficient enough to support the loading coming into the airport for the next 30 years. And then two alternatives were run. Again, the alternatives were reconstruction of the current pavement at the airport, and then the other one is also using an overlay. That concludes my presentation for this research paper. Thank you.